Hello people, Zach here again today, and this is going to be another video arguing against general relativity. So let's go ahead and get into this. Right here what we have is an electrical circuit where we have a DC power source and two loops of current. So first current loop goes down through here, runs through an inductor, back up and back to the power source, and the other loop goes this direction through the inductor, back up through the power source. And this, of course, is a switch which is by default closed, which allows the circuit to be completed. But the important thing about this particular circuit, even if my crappy drawing skills don't really depict it well, is that the length of this wire is the same as the length of this wire. This one is the same length as this one. This inductor is the same length as this inductor. This wire is the same length as this wire. This wire is the same length as this wire. This one is the two loops are perfectly identical. The only thing that's different is that one's mirrored. And of course, these two inductors have the exact same number of turns in their coils, which basically means that if they're both getting the exact same electrical current, and they both have the same exact wire lengths, and they both have the same number of coils, that these two inductors are going to be producing the exact same magnetic field strength. Now, below these two inductors, what we have are these two magnetic weights. And my crappy drawing skills aside, these two weights are supposed to have the exact same size, the exact same shape, and the exact same mass. And they have these little magnetic, parts up here that kind of hold it up to the electromagnetic as long as the circuit's closed. Now, below the circuit, we have this man who's standing. And the question is, when we open the circuit, which cuts off the electrical current, what is this guy going to see? Well, what he's going to see is these two weights are going to be falling towards the ground, specifically at an increasing rate of 9.8 meters per second squared, which is Earth's gravitational force. But here's the question. What is this guy going to be observing? He's basically has his feet tethered to this rod, and maybe he's rigid so he can't really flop around or anything. But what is he going to be observing from the other mass over here? And the answer is going to be nothing. From his perspective, this thing is not accelerating at all. It's basically at rest, because he himself is accelerating at the exact same rate. At best, what you could argue is that there's a gravitational force between these two masses that are kind of pulling them together, and that particular force might, if he has sensitive enough equipment, might register to him as a downward force from his perspective, where the object is accelerating towards him. But even then, he's not registering this downward path. At best, he sees straight coming towards him. So, now, general relativity says that accelerations are universal, which this experiment obviously disproves. But building off from there, I want to talk a bit about forces. So, the first thing we want to talk about is Newton's laws of motion. The very first law of motion is that an object at rest remains at rest unless acted upon by a force, and an object in motion moves in a straight line at a constant speed unless acted upon by a force. Now, when these two things are in free fall, this guy, from his perspective, this thing is at rest because it's not moving relative to him at all. And so there's no reason why it would actually change unless it was exerting a force. And which is, like I said, if there was a gravitational force between these two masses, then this object would cease to remain at rest. And so he would register that there is a force between him and that object. Now, the fact that he can't tell that there is a force between the mass and the ground here does not mean that the force doesn't exist. Basically, it just means he can't perceive it. The only way that you can perceive a force is by the effects of the force, which is the acceleration, which in turn causes the displacement. So if you don't see anything moving, if things seem like they're at rest, you don't really know if there's a force on it. And bear in mind that forces, according to Newton's laws of motion, the third law of motion, for every force there's an equal and opposite force. Now, normally when we think of a force, what we think of is as a force vector. But remember, he said there's an equal and opposite force, so there's another vector going the opposite direction. So the real depiction of a force is something more like this, or more like this. But the reason why I bring this up is that although accelerations are relative to your frame of reference, forces are not. This force, regardless of whether or not he can perceive there being a force between these two, this force will still exist. Now, the second he perceives it, then obviously he knows that it's there, but it'll be there nonetheless. Even for this guy down here at the bottom of the ground, where he's seeing both objects fall, for him, the force between these two things would still exist. The thing is that forces are universal. They are in every frame of reference, but your ability to quantify those forces is relative. And I think that this is one thing that maybe Newton was trying to get at, that people just misunderstood, because they're so concerned with motion that they're not understanding that the universality applies to the forces, not the motions. All forms of motion are relative, but forces themselves are universal. And of course, this goes against general relativity's idea, which is that accelerations are relative. But anyway, I just really wanted to cover this because I've had this discussion with numerous people in one of my previous videos. And I think I'll just go ahead and leave it there. Thank you for watching.